Okay, let's jump right in today. We're looking at a paper called FastGS, Training 3D Gaussian Splatting in 100 Seconds.
Yeah, this one's generating some buzz from Ren, Wen, Fang, and Liu at Nankai University. And that title, well, it doesn't lie.
Sub-100-second training for 3D Gaussian splatting on, like, complex scenes. That's a pretty big claim.
It really is. FastGS is basically a general acceleration framework. They managed to train the tanks and temples scene in, under 100 seconds. Well, about 1.3 minutes, actually.
Okay, so what's the magic here?
It comes down to a new way of handling the Gaussians themselves. They call it VCD and VCP. It's a densification and pruning strategy based on multi-view consistency.
Multi-view consistency. Okay, so not just optimizing the code pipeline, but fundamentally changing how Gaussians are added and removed.
Exactly, and the results speak for themselves. They're showing up to, 3.32 times faster than Gaussian on Mibner R360.
Wow, and Gaussian was already considered pretty fast state-of-the-art.
Right. And importantly, they do this while keeping the rendering quality comparable. Plus, they end up with way fewer Gaussians at the end. Much more compact model.
Fewer Gaussians is a big deal for deployment, right? Less memory, faster rendering.
Definitely. And they show this isn't a one-trick pony either. FastGS gives like 2 to 7 times acceleration across different, more complex tasks to dynamic scenes, surface reconstruction, even SLAM.
So it seems quite general. This could really tackle that training bottleneck we still see with 3DGS.
Yeah, absolutely. I mean, novel view synthesis, NVS, it's so important now, isn't it? For AR, VR, autonomous driving simulation, you name it.
And 3DGS was already a huge leap from NERF, which took hours, sometimes days to train. 3DGS brought it down to tens of minutes.
Which was great, a massive improvement. But, for truly interactive applications, user-facing stuff, tens of minutes is still, it's a barrier.
It's the difference between a cool research demo and something you can actually ship, right?
Yeah. Precisely. So the authors looked hard at why 3DGS still takes that long. And they found it wasn't just the rendering pipeline, though others have worked on that. The real inefficiency, they argue, is in the adaptive density control, the ADC.
ADC, right. That's the part that decides when to add more Gaussians, like splitting or cloning them, and when to prune the ones that aren't useful anymore.
Exactly. Densification based on positional gradients, and pruning based on things like low opacity or being too big.
So where does that standard ADC process go wrong, according to this paper?
It leads to what they call excessive redundancy. Basically, it creates way too many Gaussians that don't actually help that much. Even the faster methods like taming 3DGS or Gaussian, they try to put a budget on Gaussian growth, but they don't really fix the root cause. They don't properly regulate which Gaussians get added or kept.
So they're still relying too much on that local gradient signal, like, oh, big gradient here, let's split, without checking if it actually improves the view from multiple angles.
You got it. They reference figure 2 in the paper, showing how the number of Gaussians just explodes over training iterations with these other methods.
Right.
They argue that these methods often rely on scores related to the Gaussian itself, rather than its actual contribution to the final rendered quality across multiple views. So you get weak multi-view constraints, or sometimes, like with Speedy Splat they mentioned, you actually lose rendering quality to gain speed.
Okay, so the core problem is adding and keeping Gaussians that aren't truly necessary from a multi-view perspective.
Which leads us directly to the FastGS philosophy, the big idea.
Multi-view consistency. You mentioned it earlier. It sounds almost like something from traditional 3D reconstruction.
It is. They explicitly draw a parallel to bundle adjustment. But the core insight is simple, but powerful. Every single 3D Gaussian must demonstrate multi-view consistency.
Meaning
it has to actually improve the rendering quality across several different viewpoints looking at the same part of the scene. It needs to justify its existence, geometrically speaking.
So instead of just reacting to a 2D gradient in one view, you're enforcing a proper 3D constraint. Does this Gaussian make sense in the 3D world represented by all these images?
Exactly right. And because this constraint is so much more effective at controlling density, they found they could completely get rid of the budgeting mechanisms that other methods use. It's surgical.
Okay, let's break down how they implement this. First, the densification part, VCD, multi-view consistent densification. How does it work differently from the old gradient method?
So vanilla 3DGS just looks at the gradient magnitude. High gradient, maybe split. VCD asks a different question. Is this region consistently poorly reconstructed across multiple views?
How does it check that?
It samples a small number of training views, k equals 10 in the paper. For each Gaussian, it calculates an important score, Let's call it S plus I.
And this score measures?
It measures the average number of high-error pixels that fall within that Gaussian's projected footprint across those 10 sampled views.
Okay, so if a Gaussian covers an area that consistently looks wrong from different angles, its score goes up.
Precisely. And high error here is defined simply using the per pixel L1 loss between the ground truth image and the rendered image. They normalize it, threshold it, and that gives them an error mask.
Got it.
A Gaussian only gets densified, split, or cloned if its importance. Score S plus I is above a certain threshold, tau plus. This ensures they only add geometry where there's a persistent multi-view confirmed need for it.
That makes a lot of sense. It stops the uncontrolled growth based on noisy single-view gradients. What about the other side pruning? VCP, multi-view consistent learning. Pruning's always tricky, right? Prune too aggressively and quality drops.
Definitely. Vanilla pruning based on opacity or scale can be quite crude. VCP aims to be smarter by calculating a pruning score, S minus I, that directly measures how much a Gaussian contributes to the degradation of rendering quality.
Contribution to degradation? How do you quantify that?
It's a clever score. It combines two things. First, like VCD, it looks at the count of higher pixels within the Gaussian's footprint across sampled views. But second, it also incorporates the overall photometric loss of those views using both L1 loss and SIM.
Ah, SIM. So it's considering structural similarity too, not just pixel-wise L1 difference.
Exactly. It looks at the broader impact on image quality. So the score essentially asks, if we remove this Gaussian, how much worse would the L1 and SIM metrics get across these multiple views?
I see. So if the score is low, removing it doesn't really hurt the overall multi-view quality, meaning it's genuinely redundant.
Precisely. If the score S minus I exceeds the pruning threshold, tau minus, then boom, the Gaussian is pruned. It ensures you only remove primitives that truly aren't pulling their weight in the multi-view reconstruction.
So VCD stops unnecessary Gaussians being added. VCP removes the ones that aren't contributing effectively. That seems like a really solid foundation for controlling density.
It is. And they added one more piece, a smaller module called Compact Box, or CB. This one focuses more on the rasterization efficiency.
Okay, what does CB do?
It tackles a different kind of redundancy. The standard rasterizer can generate a lot of Gaussian tile pairs that don't contribute much to the final pixel color. CB prunes these low contribution pairs based on Mahalanobis distance.
So it cleans up the rendering pipeline itself a bit?
Yeah, it reduces unnecessary computation during rendering. It's not the main density control like VCD-VCP, but it gives an extra little speed boost while maintaining quality.
So VCD and VCP handle the model compactness, CB helps the pipeline speed. Let's talk results then. You mentioned the Mipner 360 numbers earlier.
Right. On Mipner 360, which is a pretty standard benchmark, FastGS trained just 1.92 minutes.
1.92 minutes? Compared to Gaussian?
Gaussian took 6.38 minutes on the same data set. So yeah, that's a 3.32x speed-up number. And on Tanks and Temples, they hit that 1.32 minute mark. Really fast.
And the model size comparison is stark, isn't it? I remember seeing that graph.
Oh, absolutely. Figure 2 in the paper is quite telling. FastGS maintains a much, much lower number of Gaussians throughout the entire training process compared to others.
What were the final numbers on Mipner 360 again?
For FastGS, the final model had only 0.38 million Gaussians. Gaussian ended up with 2.40 million.
Wow, nearly 7 times fewer Gaussians. That's incredible efficiency. It really shows VCD and VCP are doing their job.
It does. And they also explored that typical trade-off between speed and quality. They have a variant called FastGS Big.
FastGS Big, what's the deal there?
It trains a bit longer, around 3.59 minutes on Mipner 360. Still way faster than Gaussian, mind you.
Yeah.
But the interesting thing is, this slightly slower version achieved the highest overall rendering quality, better PSNR and SIM than all competitors, including Gaussian.
So the multi-view consistency approach doesn't just make it faster and smaller, it can actually lead to a better final representation if you give it a little more time.
Seems that way. It suggests the underlying principle is fundamentally sounder for achieving high fidelity.
Okay, for people listening, engineers and researchers, a key question is always generality. Is this FastGS approach locked into one specific setup, or can it be applied more broadly?
That's one of its biggest strengths, I think. Because it's based on this core geometric principle of multi-view consistency, it's not tied to a specific implementation detail. It's portable.
So they tested it with other 3DGS backbones?
They did. They plugged FastGS into things like 3DGS Excel, MIP Splatting, ScaffoldGS, and they saw significant speed-ups and model size reductions across the board.
Any specific examples?
Yeah, combining FastGS with MIP Splatting on Mipner 360 brought the training time down to just under 3 minutes, which was a 2 to 14 times speed up depending on the scene, and it reduced the Gaussian count by an average of like 77%.
That's pretty convincing evidence of its general applicability within static NVS. What about more complex scenarios?
They pushed it further. They applied it to dynamic scene reconstruction, integrating it with deformable 3D GS. Got a 2.6x speed up there.
Okay.
And for surface reconstruction, using methods like PGSR, they saw 2 to 7 times acceleration when FastGS was added. This really underlines that the method leverages fundamental 3D principles, not just task-specific tricks.
That's crucial. Let's quickly touch on the ablation study. Did they confirm the individual contributions of VCD and VCP?
Yes, they did. The ablation on MIBNR 360 was quite clear. VCD by itself, just the consistent densification, resulted in nearly 3 times faster training and an 80% reduction in Gaussians compared to the baseline 3D GS.
80% reduction just from smarter densification. That really highlights how much redundancy the standard method creates.
It really does. And VCP on its own, the pruning part, it cut training time by almost half and reduced Gaussians by nearly 30%.
Also significant, showing it effectively removes the fat without hurting quality.
Exactly. And then putting VCD, VCP, and that little CB module together gives you the full FastGS result, that impressive 1.92-minute training time.
Okay, so wrapping up the core contribution here, FastGS seems to nail the training time problem in 3D GS. It replaces that older gradient-driven density control with this multi-view consistency idea.
Which is, more sophisticated conceptually, but apparently simpler and more effective in practice. Leading to state-of-the-art speeds, we're talking sub-100 seconds on key benchmarks and these really compact, efficient models.
Which is exactly what you need for real-world deployment in AR, VR robotics.
But even with this big step forward, the authors are clear that there's still work to do. They point out a couple of areas for future research.
Oh, what are they looking at next?
Well, first, even though it's fast, it still requires 30,000 optimization steps. So finding ways to make the optimization converge even faster, needing fewer steps, is one direction.
Makes sense. Less optimization means even quicker results. What's the second area?
The second one is maybe the bigger challenge, getting rid of the cull-on-up initialization step.
The structure from motion preprocessing. That still takes time, right?
It does. It's often the bottleneck before 3D GS training even starts. So they suggest developing a general feed-forward NVS model that could potentially replace cull-on-up entirely, eliminating that whole initial pose estimation phase.
That would be huge. True instant scene capture and rendering.
That's the dream, isn't it?
Yeah.
But coming back to FastGS itself, the really interesting takeaway for me is how they achieved this speed up by looking back at classical 3D reconstruction principles, like that bundle adjustment analogy.
It's a great example of bridging the gap between traditional computer graphics and modern neural rendering.
Definitely.
And that brings us to a final thought for you, the listener, to maybe mull over. FastGS showed that applying a core principle from classical 3D geometry multi-view consistency was the key to dramatically simplifying and speeding up Gaussian density control. So the question is, what other fundamental principles from traditional graphics or computational photography, maybe ideas from advanced ray tracing, light transport, or perhaps camera calibration techniques could be adapted next? Could borrowing more from the old school be the key to unlocking further breakthroughs in efficiency and capability for other complex neural rendering tasks beyond just 3D GS? Something to think about.